Welcome to the deep dive. We've got your sources here, and today we're digging into the history of natural language processing, NLP.
That's right.
If you're curious how computers went from just numbers to, well, starting to grapple with human language, this is for you. We're aiming to give you that shortcut understanding of where this huge field came from.
And, understanding the history isn't just trivia. It really helps you appreciate what these systems can do now.
And what they can't do, maybe.
Exactly. The challenges, the potential. It's been a long journey, definitely not a sprint. Layer upon layer.
Okay, so let's get on the same page first. NLP, natural language processing. What is that, fundamentally?
At its core, it's the part of AI that tries to bridge the gap between human language and computers.
So making computers understand us and maybe talk back.
Precisely. Enabling machines to understand, interpret, and even generate human language, text, or speech. Teaching them to listen and speak.
And your sources break this down, right?
Yeah.
Into understanding versus generating.
Yeah, that's a useful distinction. You've got natural language understanding, NLU, that's the interpretation part.
Going beyond just words.
Right.
Getting the deeper meaning, the context, figuring out intent, pulling out specific things like names or places, understanding sentiment, basically turning our messy, unstructured language into something structured a computer can work with.
Okay, so NLU figures out what I meant. Then what about the computer responding?
That's natural language generation, or NLG, taking structured data and producing, human-like language from it, text or speech.
Can't sound natural.
Yeah, making it coherent, relevant. The sources mention steps like figuring out what to say, how to structure it linguistically, and then actually rendering it.
Got it. NLP is the umbrella. NLU understands, NLG generates. So let's dive into this history. You mentioned it goes way back.
Oh, yeah. Way, way back. Before electronic computers were even a glimmer. We're talking philosophical ideas first.
And the sources point to Gottfried Wilhelm Leibniz, 17th century. That's really early. What was he thinking about? While Leibniz had this incredibly ambitious vision, he dreamt of a universal symbolic language, the characteristica universalis.
A language for everything.
Basically, yeah. To represent all human knowledge perfectly, without ambiguity. And then a calculus ratiocinator, a kind of automated reasoning system using that language.
Wow. Like an alphabet of human thought, the sources say.
Exactly. He thought disputes could just be calculated away if we had the right symbols and rules. It's like a very early blueprint for AI goals.
Formalizing language, automating reason.
You got it. But his struggles also highlighted just how messy and ambiguous real language is, a problem that would crop up again and again.
And he worked on binary math too, right?
Yeah.
Kind of laying groundwork.
Indirectly, yes. His work on binary and mechanical calculators connects to the machines that would eventually try to tackle these language problems.
Okay, fast forward a bit. The sources make a surprising link to the Enigma machine. World War II code breaking. How does that fit?
Well, Enigma wasn't about understanding language, obviously. It was about automated language transformation, encryption.
Just scrambling it up.
Right. But the massive effort to break Enigma, led by people like Alan Turing with his bomb machine, pushed computation and cryptanalysis forward massively.
So the need to analyze that coded language drove innovation.
Absolutely. All that work on pattern recognition, statistical analysis of sequences, automating symbolic manipulation, it's conceptually linked to later NLP. It showed computation could tackle language-like data.
And speaking of Turing, he comes up again right after the war, 1950, with the Turing test. That feels much more direct.
Oh, definitely.
Yeah.
His paper, Computing Machinery and Intelligence, shifted the whole debate. Instead of, can machines think? He asked, pragmatically, can a machine imitate a human in conversation well enough to fool someone?
The imitation game.
Exactly. Suddenly, language ability became this key benchmark for intelligence. Could it talk like us?
That really puts language front and center for AI.
It did. It gave a way to measure progress. Even if the test itself has limitations we understand now, it cemented language processing as a core AI challenge.
And just before Turing, 1949, Warren Weaver's Memo on Translation. This sounds like the start of machine translation, MT.
It really is considered a foundational text for MT. Weaver saw translation as a kind of cryptography problem, like decoding.
Before computers were even common.
Yeah, quite visionary. He talked about using context to figure out word meanings, even linguistic universals between languages.
I must have sparked a lot of interest.
Huge interest. It helped get early funding and research going, a great example of cross-disciplinary thinking, but maybe also a bit overly optimistic about how easy translation would be. language is tricky.
So this early period, pre-1950s, we've got Leibniz dreaming of universal languages, Enigma driving computation through code breaking, Weaver aiming for machine translation, and Turing setting language as the benchmark for intelligence.
That's a good way to sum it up. Different threads, but all pointing towards this idea that machines could somehow process human language. It set the stage.
Which leads us right into the next big phase, the symbolic era. Roughly 1950s to late 80s. This is the good old-fashioned AI time, right? Joe FAI.
That's the one. The main idea here was, okay, let's figure out the rules of language, the grammar, the logic, the vocabulary, and explicitly program them into the machine.
Like teaching it grammar rules from a textbook?
Kind of, yeah. Hard-coding linguistic knowledge and reasoning structures. If we give it enough rules, maybe it can understand.
Let's look at some examples. The sources mention the Georgetown IBM experiment pretty early on, 54.
Right. A very early, a very famous demo. They translated about 60 Russian sentences into English using an IBM mainframe.
60 sentences, that doesn't sound like much.
It wasn't, and the system was very limited, small vocabulary, simple grammar, probably carefully chosen sentences. But the impact was huge.
It generated buzz.
Oh, yeah. Loads of hype. Got funding flowing into MT research worldwide. A classic case of a proof-of-concept demo driving a field, even if it set some slightly unrealistic expectations.
Okay, moving to the 60s. ELIZA. That one's pretty well known. The therapist program.
ELIZA, from Joseph Weissenbaum. It simulated a Rogerian therapist using a script called Doctor. The goal was interaction, making it seem like it understood.
How did it pull that off? Did it actually understand?
No, not really, and that's the crucial part. It used simple pattern matching. You type something, it looks for keywords, uses a pre-programmed rule linked to that keyword to spit back a response.
Like, tell me more about X.
Exactly. Stuff like that. It wasn't understanding meaning, just manipulating text based on surface patterns.
People thought it did. The ELIZA effect.
Precisely. People projected understanding onto it. It was fascinating, showed how easily we anthropomorphize, how compelling even simple interaction can be. A benchmark for chatbots, but also a warning about mistaking surface fluency for real comprehension.
Then there was SHRDLU. That sounds like a step up in actual capability.
SHRDLU from Terry Winograd in the late 60s, early 70s was definitely a leap. It operated in a constrained environment, a simulated blocks world.
Little virtual blocks on a table.
Yeah. And within that world, it could do amazing things. You could tell it, kick up the red block on top of the blue pyramid and put it in the box.
In natural language.
Yes. And you would parse the sentence, figure out which block you meant, understand the relationships on top of, plan the actions, and actually do it in the simulation. It integrated language, understanding, reasoning, planning, the works.
So it genuinely seemed to understand in that little world.
Within that micro world, absolutely. It was a landmark achievement for Joe FAI, showing what was possible with symbolic rules and logic in a limited domain. Really exciting stuff.
But the real world isn't a neat little blocks world. That's where this approach ran into trouble, wasn't it?
That's the killer insight, yeah. Trying to scale that rule-based approach up to the complexity and messiness of general human language, it just didn't work. The limitations became painfully clear.
What were the big roadblocks? Why couldn't they just keep adding more rules?
Well, first, these systems were incredibly brittle, fragile, meaning real language is full of slang, typos, unexpected phrasing, nuance. If the input wasn't exactly what the rules expected, the system would often just break, fail completely, couldn't handle variation or errors gracefully.
Okay, so very rigid.
Very. Second, scalability. Just think about how many rules you'd need to cover all of English or any language. It's astronomical. The complexity explodes. Building and managing that massive rule base. Impractical, impossible, really.
And someone had to write all those rules by hand.
That's the third issue. Massive manual effort. Linguists and programmers painstakingly crafting rules. And the systems were static. They couldn't learn from new data unless someone manually updated the rules. Slow, expensive, error-prone.
And ambiguity. Language is full of words with multiple meanings, sentences you can read multiple ways.
Exactly. Handling ambiguity was a huge struggle for rule-based systems. They lacked a good way to figure out the most likely meaning and context. How do you write a rule for that? It often needs statistical likelihoods.
These sound like deal breakers.
Yeah.
And there was a big setback around this time, right? The ALPAC report.
Yeah, ALPAC 1966, a U.S. government report looking into machine translation progress, mainly for translating Russian during the Cold War. And it was pretty scathing.
What'd I say?
Basically, that MT was slow, expensive, and not much better than human translators. They criticized the lack of fundamental research in computational linguistics.
Ouch. What was the impact?
It led to major funding cuts for MT in the US, really put a chill on things, contributed to an AI winter for NLP. Progress slowed down.
Any silver lining?
While some argue it forced the field to step back and focus on more basic foundational research, build a stronger theoretical base before trying to build complex systems again. Maybe it set the stage for the next phase, indirectly.
And from a business perspective during this whole symbolic era, lots of ideas, but not much real-world application yet.
Pretty much. People saw the potential, sure, automated assistance, information analysis, but the tech just wasn't ready for prime time. Computers were too slow and expensive, not enough digital data, and these rule-based systems were just too brittle and hard to scale for complex, real-world business problems.
So a lesson in needing the tech, the data, and the right approach to mature together.
Exactly. You need more than just a clever idea or a cool demo. You need robustness, scalability, cost-effectiveness, the whole package.
Which brings us to the next major shift, a real revolution starting late 80s, early 2000s, the statistical revolution, moving away from rules entirely.
A complete paradigm shift. Instead of trying to tell the computer the rules of language, the idea became, let's give it tons of real language data, text, speech, and have it learn the patterns, the probabilities, the statistical associations automatically.
So rather than coding adjectives often precede nouns, you just show it millions of sentences, and it figures out that adjective-noun is a likely pattern.
Precisely. It's data-driven. Models like n-grams, hidden Markov models, statistical parsers, they learned likelihoods from massive text corpora.
And this needed those large data sets.
Absolutely critical. The availability of things like the Brown corpus, digitized parliamentary records like the Canadian Hansard, that was the fuel. The techniques, the data, and growing computer power all came together. It became much more empirical.
So what was the big win here? Why was this statistical approach better than rules?
The number one advantage was robustness. Because these models learned from real, messy data, they were much better at handling the variations, the noise, even the errors you find in actual human language. They weren't so brittle.
They could cope with language as it's actually used.
Much better, yeah. They were also more adaptable and scalable. Need to handle a new domain, get data for that domain, and retrain the model. Way easier than rewriting thousands of rules. And you could often improve performance just by adding more data or tweaking the model.
Less manual effort in building the system itself.
Definitely shifted the effort. Less hand-coding rules, more focus on preparing data, choosing models, engineering features, but still needing linguistic insight. And ambiguity resolution got much better.
How so?
By using probabilities. The models could look at the context and assign likelihoods to different possible meanings or structures, choosing the most probable one based on what it learned from the data. Much more nuanced.
And do they just work better overall?
For many tasks, especially with enough data, yes. Statistical systems started outperforming rule-based ones in benchmark evaluations. It also started to democratize the field a bit, bringing in skills from statistics and machine learning alongside linguistics.
Okay, let's talk specifics.
Yeah.
Hidden Markov models, HMMs. You mentioned those are big, especially for speech.
HMMs were huge. They're great for modeling sequences where you have underlying hidden states like the foam someone is saying that generate observable data, the actual sound waves.
How did that help speech recognition?
It became the dominant technique for ASR from the late 70s, early 80s onward. Pioneers like Baker and Jelinek applied HMMs to model speech sounds. By the early 90s, this led to the first practical, large vocabulary systems you could actually use, a massive breakthrough.
And they work for text, too, like part of speech tagging.
Yeah. Mid-80s onwards, HMMs were used to figure out the most likely sequence of grammatical tags. Noun, verb, adjective for words in a sentence, learning the probabilities from annotated text. Very effective. The success of HMMs was really a proof of concept for the whole statistical paradigm, helped pull NLP out of that post-Allopac slump.
Statistical machine translation, SMT, was another big one. IBM's Candide system.
Right. Candide, late 80s, was revolutionary for MT. No linguistic rules. It learned how to translate by statistically analyzing huge amounts of parallel text.
Like documents already translated between English and French.
Exactly. Like the Canadian Hansard records. IBM developed complex statistical models to figure out word alignments, phrase probabilities between languages. You feed it aligned sentences, it learns the statistical mapping.
And that worked better.
Significantly better for large-scale systems. More scalable, often better quality than the rule-based systems of the time. It powered the first generation of widely used online translation tools, a whole different ballgame.
Information retrieval, finding relevant documents, also fits in here.
Absolutely. IR deals with large text collections, so statistical methods were a natural fit. While early ideas existed, this era solidified techniques like the vector space model.
Where documents are represented as vectors.
Yeah, pioneered by Gerard Sultan. Documents and queries become points in a high-dimensional space based on the words they contain, often weighted by TF-IDF to measure importance. You find relevant documents by seeing which ones are closest to the query vector using things like cosine similarity.
Sounds like the basis for search engines.
It absolutely is. And initiatives like the TRC conferences starting in '92 were crucial. They provided standard test collections and metrics, driving competition and empirical progress in IR. Showed the power of statistics for information access.
So this statistical era is really when NLP started showing up in everyday life.
This is where the rubber met the road, definitely. Search engines transformed everything, built directly on statistical IR.
And spam filtering. That got so much better.
Huge improvement. Moved from simple keyword rules that spammers quickly learned to evade to statistical classifiers like naive Bayes. Trained on examples of spam and non-spam, they learned the statistical signals of junk mail much more effectively. Solved a massive headache for everyone.
Things like spell check, predictive text on phones, too.
Yep, all benefiting from probabilistic language models developed during this time. Practical, useful applications became widespread.
So business relevance went from potential to actual massive value.
Truly. The tech was finally robust and scalable enough to tackle real problems effectively. Search and spam filtering weren't just incremental improvements, they enabled new ways of working and communicating. Big lesson. Mature tech meeting real needs equals major impact.
Okay, building on that statistical success, we enter the machine learning era, say early 2000s to mid-2010s. This seems like taking those statistical ideas and applying more general machine learning algorithms.
That's a good way to think about it. It was a period of maturing statistical methods, but really leveraging established ML algorithms. And a huge part of this era was feature engineering.
Right. What does that mean for text? Getting the text ready for the algorithms.
Exactly. It's the whole process of selecting, transforming, and creating informative features from the raw text that an ML algorithm can actually learn from. It was often the most critical part of getting good results, required a lot of skill and linguistic intuition.
What kinds of features are we talking about?
Things like bag of words, just counting words, ignoring order, n-grams to capture short sequences, TF-IDF scores for word importance, adding grammatical info like part of speech tags, maybe features from syntactic parsing, identifying named entities knowing apple is a company, not just a fruit, using stemming or lemmatization to group word forms.
So manually crafting these indicators from the text for the ML algorithm.
Pretty much. Trying to distill the relevant linguistic information into a numerical or categorical format the algorithm could crunch.
And which ML algorithms were popular then?
Well, support vector machines, SVMs, were very popular for classification tasks like sentiment analysis. They're good with high-dimensional data like text represented by lots of features. People use them to classify product reviews, tweets, things like that.
Naive Bayes still around?
Oh, yeah. Still a workhorse for text classification, spam filtering. Simple, fast, often works surprisingly well.
Logistic regression.
Yep. Often called maximum entropy or FACSINT in NLP circles. Widely used for classification, tagging, and named entity recognition. A solid discriminative model.
Decision trees.
Used sometimes, especially because you could interpret the rules they learned, but maybe less robust or accurate than SVMs or Maxent for some text tasks, and could overfit easily if you weren't careful.
So applying standard ML toolkits to text, but heavily reliant on crafting good features. Did these features capture everything, though? Like deep meaning?
And that's the key limitation your sources point out. These features, bag of words, n-grams, basic tags, they're considered shallow. They capture word presence, local patterns, surface grammar, but they struggle with deeper semantics.
Like understanding synonyms or sarcasm or complex relationships?
Exactly. They don't really capture meaning in a rich way. This put a kind of ceiling on what systems based purely on these features could achieve. It really highlighted the need for ways to learn richer, denser representations of meaning directly from data. which sets the stage for later developments.
And during this time, NLP also got easier for people to actually use, right? Toolkits.
Huge development. Libraries like NLTK, the Natural Language Toolkit, starting around 2001, were game changers, especially for education and research.
Made it easier to experiment.
Massively. It's a Python library providing easy access to tokenizers, stemmers, taggers, parsers, classifiers, the basic building blocks. The NLTK book became a standard, really lowered the barrier to entry.
In Stanford Core NLP.
Core NLP from 2010 was more like an industrial-strength integrated pipeline, gave you high-quality results for a whole chain of analysis, sentence splitting, tagging, parsing, entity recognition, core ofference, sentiment, all packaged together. Made it much easier to build applications needing sophisticated linguistic analysis.
So this era really consolidated the ML approach, focused on feature engineering, but also made the tools much more accessible.
Right. It built on the statistical revolution, applied established ML techniques, pushed the boundaries of what shallow features could do, and democratized access to core NLP technology. Ready for the next leap.
Wow. Okay, what a journey. From Leibniz's philosophical dreams and code breaking through those early brittle rule-based systems like ELIZA and SHR-DLU.
Then the huge shift with the statistical revolution, learning from data with HMMs, SMT, vector spaces.
And finally, refining that with established machine learning algorithms and feature engineering while making tools like NLTK available.
It's really been this incredible layering process. New ideas, building on old ones, overcoming limitations, powered by more data and faster computers each step of the way.
So if you're listening to this, what does all this history mean when you use, I don't know, a search engine or see spam filtering work?
It means those things you probably take for granted didn't just appear. They're the result of decades, even centuries, of thinking, trying, failing, learning, all this work we've just talked about. That journey from rules to statistics to machine learning is why those tools work as well as they do.
It moved NLP from the lab into practical everyday use.
Absolutely. But, thinking about that whole journey, especially the shift from explicit rules to learning statistical patterns, it leaves you with a really interesting question. Are these systems truly understanding language like humans do?
Or just getting incredibly good at finding correlations in the data.
Exactly. Are they mastering statistical relationships or grasping meaning? That distinction, between mimicking understanding through patterns like Eliza did in a simple way and genuine comprehension, that's still a central question in AI today. It makes you think about what understanding even means, doesn't it?